Thank you, Andrew. Hi people, my name is Avinash Shankaranarayanan and I'm from India. This presentation is basically going to try and enlighten you about biomass and how we try to provide heating by avoiding this kind of technology. This is a boiler unit that you're looking at. The thing here is a boiler is used to heat the hot water in this particular agricultural school. And yeah, if you look at the slide closely, there are two types of boilers that's installed here. The first type is 5.4 liter, and the second one is 7.9 liter. This is per hour. The usage of fossil fuel here is in the form of kerosene, right? So kerosene is used here, and we have somewhere around 9,600 to 10,000 liters used every year in the school. So this is a big problem. We're using fossil fuel and we're paying for it. So we're going to look at some technology that's going to help us find out how we can avoid this old technology and replace it by using CHP and biogas. If you look at this slide closely, it shows the potential that's available in this school. And the potential here is about 180,000 kilowatt hour per annum. We're looking at an investment of 32 million for installing a biogas plant and a CHP system with it. We're looking at 26 kilowatt peak, which is the installation capacity. This is the thermal potential, in other words, the heat that can be utilized in the system. And we are assuming that 30% of this is used by the system itself. We have bio-waste, which is about 800 tons per annum. And we have about 8.7 million Japanese yen savings by using this system. Okay? We have about 50% prefecture subsidies, which means the government is interested in financing 50% of the total investment. Now, before we go into other slides, what's important here is we need to understand what is biomass? What are we trying to do here? Why is it so important? We need energy to move around every day. A person runs and comes back home, he has to eat something so that he can replace his energy that's lost, right? So we eat vegetables, we eat meat, we eat a whole lot of things. And everything that we eat has a specific calorific value. It's energy. And this is the energy potential that we are losing when we are cooking. So for instance, if you take AP House, I was talking to Justin yesterday, we throw a lot of food. There's a whole huge amount of food waste, right? In form of vegetables, and this is what we call as biomass. This energy that's thrown is what we would like to put into a closed loop system so we can generate electricity and heat, right? Next slide. So I'm going to explain how this thing works. This is basically a blueprint diagram of what Peter was showing before. It's another simplified diagram here. You've got biomass, which is basically food waste and waste that come from agriculture. For example, cow dung is a good example here. This is then put into a primary pit, where this is just a storage area. You're storing your biomass. And then you're transferring this to something called a digester. Now, to make it very clear, a digester is a simple unit where you just put all your biomass in, and then you close the lid and make sure there's absolutely no oxygen. All right? Once you leave this digester unit and it gains heat, right? This digester unit starts to emit methane, which is CH4. So this methane is gas which is burnable. It's clean energy. This is the energy that's lost when we throw biomass outside, the garbage that we generate every day. So once we got this CH4, we can use a gasifier unit to create energy. Basically, you burn through combustion, and then you get this energy out. Now, because I'm mentioning the word burning here, or combustion, we have heat. There's a huge amount of heat that's going to escape from your generator. So we want to make sure we utilize this heat to the maximum extent. So in other words, we take this heat, put it in a heat exchanger, basically capture this heat, and we try to use it in the school. And what do we need this heat for? Japan is a cold place, especially during winter. We can use it for heating homes. We can also use it for other purposes like hot water, and where we're using a lot of electricity just to boil water, we might use this heat there. So I'm going to show you a calculation how this works and what's the economic benefit and ecological benefit at the same time. This is the equipment that's in use. Yeah, We've got water storage tank to store the hot water in. We've got 2 units of heat exchanger in it, insulated pipeline. This is quite important because if you do not have proper insulation, you're going to lose energy. And we don't want to lose energy. Of course, every system has some form of losses which has to be accounted for, right? So we've got 2 water pumps, which is going to pump your hot water back into the system. The total investment that we're looking at is somewhere around 1.2 million Japanese yen. This is just for procuring the equipment. Slide. And this is the fact sheet that we generated from calculating what kind of biomass is available in the school. How much tons of waste is available which can be converted into useful energy. So if you look at it, you've got the efficiency value, which is 40%. We can generate 40% electricity from the waste that we have. 40% is heat, right? So the total efficiency of the system is about 80%. Now, the entire 80% cannot be utilized completely, but we have some losses here and there. So we're going to show you how this works. Animal manure. So in this school that we went, we have pig farms, we have cow stables, and they're generating a lot of waste. And they already have an existing composting plant, so they use composting. Now the big problem with composting is that when you put your waste outside, it's going to smell. It's going to give you a lot of odor. And this is a big problem. You don't want that. So if you put this in a biogas plant, it's a closed system. There's no odor. In other words, you're trapping all the gases and all the odor in it so that it can be dissolved by the bacteria and it's converted into methane. This is our useful factor here. So 1 ton of biogas is 50 cubic meter. So we generate about 40,000 here. We've got 50% methane generation from this value, which is again about 20,000. And we've got an energy content in the matter, which is about 200,000, as 1 cubic meter of biogas can generate around 10 kilowatt hour. This is the electricity that we are interested in. Now, if you look at the energy conversion that's taking place here, the electricity we're generating at 40%, we're getting 40% gain from electricity, is about 80,000 kilowatt hours per annum. And if you look at the own energy demand, so which means we need to have some form of electricity so that the system can function on its own, right? This is the value. So the system uses 6,400 kilowatt hours. Yeah. So this is the kind of loss that we are looking at. If you look at the usable electricity, it's about simple subtraction. 73,600 is what we get, and we also got an equivalent amount of heat in the form of energy. What are we going to do with this heat? We can use it for cooking, or we can use it for boiling our water and giving enough heat into our system. And this is the amount of heat. So we've calculated 30% is needed by the system itself for it to function in the digester. So I was talking about the digester. We close the lid and make sure that there's enough heat so that it starts generating the biogas. Next slide. This is another part of